So last time we were talking about decision trees, and we have been alluding to random forests, which is, the forest refers to a collection of trees. And the basic idea is that you make a bunch of decision trees, like let's say 1,000 of them. And then so you train them all in the training data, and then when you want to make a new prediction, you let them vote. And the idea is that if you can do this so that each tree in the forest is wrong independently of the others, and if all of them have some tendency to be correct, even if it's very minimal, like let's say that they're right, 51% of the time. If you have 1,000 people and each one is right 51% of the time, and you have them all vote on something, as long as they're confused in unrelated ways, then if you average their opinions, then you're almost certainly going to get the correct answer. So that is the idea behind the wisdom of crowds. Like, you might have heard of this lately. It was like talked about. It seems like it was talked a lot about 10 years ago. People wrote books on it, and this woman did a TED talk where she brought a bull out on stage, and she asked the audience how much the bull weighed, and then they averaged the opinions of everybody in the audience, and it turned out to be like exactly the weight of the bull, plus or minus like a few pounds or something. So that's good. But the difficult thing is this this requirement that everybody who's voting be wrong independently of the other people. So you have a whole bunch of people who are all sort of, if their wrongness is correlated, like let's say that me and Chong, we watch all the same YouTube videos and we're into all the same like social media silos, and we read all the same websites, then if me and Chong are wrong about something, we're probably wrong in the same way. So having me and Chong vote is not going to be useful, because it's just going to be like replicating our opinions, and the error isn't going to cancel out. You need to get somebody that reads like the Drudge Report together with somebody that reads Vox, and then their their different kinds of confusion actually will cancel out, which is something that you would want to happen in democracy. This is part of the motivation for why democracy is a good system of government, and also possibly part of the reason why it seems to not be doing so well right now. It's because nobody is independently wrong anymore. It seems there are two groups of people, and both of them are all wrong in the same way, which isn't very good for the ensemble wisdom of crowds approach. So anyway, so let's look at some of the details. I have too many windows open. Is this where we are? Okay, I think so. So we'll go here to the ensemble. So we'll go through this, and I might stop and write on my notebook a little bit and say some certain things. So maybe before we talk about like ensembles of estimators that vote on different things. So by the way, both classifiers and regressors can do this. So we use the term estimator to refer to both. They use that word in the sklearn literature also. So if you have a bunch of regressors and you want them to work as an ensemble, then you just average their opinions. So the average of a bunch of continuous real value predictions, if you average them, you get another one which is centered amongst the opinions of the voters. If you have a bunch of classifiers, then you want to take not the average but the mode, and so the mode is the most common response, and it's just the let's say that there are 3 classes. It's just the class that gets the most votes. So it's not the average, but it's as if all of the classifiers in the ensemble were voting for one of the 3 classes, and then the one that you predict is the one that gets the most votes. So it gets a little bit more complicated than that. So let me open my sketchbook and set this up. Okay, so where are we here? So I want to share over there. So there's something called hard voting and there's something called soft voting. So hard voting, so let's say that we have a whole bunch of different classifiers. So say C1, I don't know, I'd rather use H actually. So H1 is one trained. So this is like a trained decision tree. After you run the decision tree learning algorithm, it outputs a single decision tree, which is a hypothesis. So we'll call this the first hypothesis, the second hypothesis, the third hypothesis, all the way down to however many hypotheses you want. So we'll use capital T for that. So that's the total number of hypotheses that you have in your ensemble. So here's an ensemble, and there are T participants. And how many classes should there be? Let's just say that there are 4 possible classes. You know, in a binary problem, there will only be 2, but let's say that there are 4. So you have class 1, class 2, class 3, and class 4. Okay, so let's say that a new instance comes along, X. So you put this X into each of these decision trees, or more generally, each of these hypotheses, and each one spits out some opinion of what class X belongs to. So they predict either class 4, class 3, class 2, class 1, etc. So just for the sake of explaining the idea, let's say that they put a 1 in the column that they think X belongs to, and a 0 in all the other columns. So this says that the first hypothesis thinks that X belongs to C2, but maybe the second hypothesis thinks that X belongs to H2, and maybe the third hypothesis agrees with C2 that this belongs here. So you might do this. You do this for all the rows, all the way down to the last one who thinks maybe, I don't know, maybe we'll have this guy have some off the wall opinion. So maybe this guy thinks that this is the correct class. So now if you sum all these up, you get a vector of you know, totals here for each column. So you know what this is depends on how people voted. In any particular column, obviously it's at most T, but we'll just make up numbers here. So maybe there's 17 votes for this one, 22 votes for this one, 9 votes for this one, and 5 votes for this one. So what we do is we take the mode prediction. So that's just the class that got the most votes, which in this case would be 22. And so this ensemble would predict that X belongs to class C2. All right, so that's hard voting. So I think a lot of the writing that I have to do to describe soft voting is already here. So let me just copy this and bring this down here. Okay. All right. So now let's talk about soft voting. So not every classifier can do soft voting because it requires the ability to assign probabilities to the different outcomes. So most classifiers can do that. All of the classifiers on sklearn, I believe. You know, in sklearn, it's the predict proba method. So there's dot predict where you can predict what a new instance which class a new instance will belong to. And there's also predict probabilities, and predict probabilities gives you a vector of probabilities that all sum to 1, and what it is H1's assignment of likelihood to the different possible outcomes. So let's say that maybe H1 thinks that there's a 0.2 chance that this new instance X belongs to class C1, and maybe there's a 0.3 chance that it belongs there, and a 0.5 chance that it belongs there, and I think I have to do 0.2 here, right? No, I have to do point. So this all has to add up to 1. So So maybe this one assigns its opinion differently. So maybe it's 0.5, 0.1, 0.1. And then what does this last one have to be? All of these have to sum to 1 because the probability that it's something is 1.
0.3.
Good, thank you. So it's 0.3, and can make up values here too. So 0.2, 0.8, 0.0, 0.0, and then all the way down to the end. So this is 0.1, 0.9, 0.0, 0.0. So then you sum all of these up, and this adds up. Let's say this first column adds up to like 10.9. The second column adds up to 12.7. Maybe this one adds up to 7.2, and this one adds up to like 1.8 or something. So now you take as the prediction, you take the class to which the greatest weight of probability was allocated. So in this case, it would be C2. So this would yield a prediction of C2 in this case. So this is using the ensemble and soft voting method. And most soft voting, it retains more information. You can always threshold soft voting just with argmax and throw away a lot of information and turn it into hard voting. So you would think that soft voting would probably work better. So by default, most things use soft voting. Okay, so let's go back to the worksheet. Yeah, the notebook. So this is just a little bit of terminology here. So ensembles, often you think of them as being made of weak learners. So a weak learner is something that is the probability that its prediction is true is better than 50%, but not necessarily much better than 50%. Okay, and this is like we've been saying, as long as each model is wrong independently of the others. This also had something to do with the financial collapse of 2008. They were issuing all these mortgages, like you might remember ninja loans, like no income, no job, no assets, and here's $300,000 and things like that. And people had come up with these financial models showing that this could like never fail. But in the financial models, there was an independence assumption that wasn't true. They were assuming that the chances that you default on your loan is independent from the probability that I default on my loan. And of course, that's not true. And everybody ended up defaulting on their loan at the same time. And that's why that was such a financial shock. Okay, so random forest is probably the most famous ensemble method. Decision trees work well with ensemble because there are easy ways to make the decision trees diverse, which is what we will be talking about in a second. And okay, so just to give a concrete example, let's look at the breast cancer data. And I saw Reagan is using a version of this data set that has only 6 columns, or it has 5 features and 1 target column. But the one that I have here has 30 columns, 30 features. One thing that's been kind of like an issue when I've been trying to help different people is I have no idea where your data set came from, and so I can't read about it. So it would be nice, just before you load your data, just put a link to the repository where you got the data, so that I can follow the link and understand what the columns mean and things like that. Okay, so we're throwing out a whole lot of information here. We're throwing out 28 features and just retaining 2. And so let's see how well we can do on this with a decision tree. So here's just your ordinary decision tree class from the sklearn library, and this one is completely unconstrained. And remember, when the decision trees are unconstrained, they have a strong tendency to overfit because it'll have zero error on the training data, because they just make a different leaf node if necessary for every single training point, and they're just memorizing the training data. So we'll see that happen here. So this is the training set. I guess it's using the entire data set here to train on. So it has 0 training error. And this is what the decision boundary looks like. And it's it's highly overfit. It's just it's built a really complex tree that has sort of leaf nodes that just pertain to very small numbers of training points. And so the variance here is very high. You can tell just by looking at this picture that if I were to sort of collect more breast cancer data, like this is like 550 data points about breast cancer. Let's say that I went out there and I collected just 600 fresh data points. And then I asked this unconstrained decision tree to come up with a decision boundary for that training data. It would probably look completely different from this one, because there might not be these 2 weird red ones might be like up here instead. So in other words, there would be high variance. Okay. So here's the training error, or sorry, the training accuracy is 1. But when you look at the accuracy on the test set, it's less than 80% accuracy. Okay, so here we're imposing some constraints on the decision tree, and I'm using grid search, what we talked about last time. I thought it would be good to go over this again because it's really relevant to project 2. You're supposed to pick three models for 3 different families. Like let's say you pick k-nearest neighbors and neural network and also support vector machine or something. So for each of those families, you need to select the best hyperparameters, and this is a really convenient way to do it. And it also uses cross-validation. So this is 5-fold cross-validation. You could, if you prefer, you could use 10-fold cross-validation. In a lot of the class notes and in previous lectures, I just used the test set as a validation set instead of using cross-validation to tune the hyperparameters, but you shouldn't do that like once machine learning is your job or something. Because you'll get optimist, you can't use the test set both for hyperparameter selection and for estimating the out-of-sample error. It has to be one of the 2. So instead we'll use cross-validation that just uses the training set to select the correct hyperparameter combination, and then we'll reserve the test set for predicting the out-of-sample error. So I do the grid search here, that tries all possibilities of, we'll try the max depth of the tree being 3, 6, or 9. Max features, you might not remember what that is, but so each node in a decision tree isn't necessarily given access to all the features. It might be only given access to some randomly selected subset of the features. So in this data set, there are 2 features, but let's say that max features is equal to 1. So then in the decision tree learning process, when you have a node and you're trying to figure out a split for the node will only have access to one of the features, which is selected at random, and then it makes its decision based on that. And then this is min weight fraction leaf is just the different possibilities for the minimum percentage of the training data that has to be at a node in order for it to be a leaf node. So 0 is the least restrictive, and 0.3 is very restrictive. This is saying that for something to be a leaf node, it has to apply to at least 30% of the training data. So it tries all those possibilities, and you can see after it tried all of those using 5-fold cross-validation, the best parameters turned out to be max depth 3, use all the features, and then just a slight restriction on the minimum weight fraction to become a leaf node. So the accuracy went up to something. It's just 88%, and the decision boundary here is much simpler. It looks as if it's just it looks like it's just one inequality based on this axis. But when you look at the decision tree itself, it looks like something a little bit more complex is happening. But still, when you just eyeball it here from 30,000 feet, it looks like it's just making a single decision. Okay, so this is the constrained tree, which has higher in-sample error. It's misclassifying these red points, but it has much better out-of-sample error because it's not overtraining on the training set. Okay, so these are the actual column names for the breast cancer data. We're kind of going to beat the breast cancer data into the ground. I really like the breast cancer data. It's like an almost ideal data set. It's high dimensional. It's easy to get high accuracy, but it's not trivially easy. And everything is numerical. There's just a lot of good things about the breast cancer data that make it good for constructing examples. Okay. So now instead of just using 2 features, we're doing the same process, but we're doing it on the entire data set. So the test score only goes up to 91.6% accuracy. This is using all of the features instead of just 2. Okay, so now we're going to introduce some ensemble methods and see if the ensemble can beat the individual tree, which of course it can. So the first thing that we're going to consider is something called bagging. And by the way, a lot of this stuff is just me sort of repeating the words of the master. Hands-on machine learning with scikit-learn and TensorFlow. So let's talk about bagging a little bit. I'm going to share my notebook again. So we'll come over here, and so bagging. So this is an ensemble method. So you're going to be training several different kinds of classifier. They don't all have to be the same kind. You could have maybe this hypothesis space is for some kind of linear classifier like the perceptron, and then maybe you have a neural network classifier, and then maybe you have a support vector machine classifier, then maybe you have a decision tree classifier, and then maybe you have I forgot what I was going to say, but some other kind of classifier. So you have several different learning algorithms here. So I've just written them as hypothesis spaces, but there's also different ways of selecting the best hypothesis too. And possibly these are all the same learning algorithm. The same hypothesis space, but you're changing the hyperparameters, which effectively changes the learning algorithm. So you have some big set of training data. So let's say XTrain. So from XTrain, you assign some training data to each one of these. So let's call this, XTrain 1 or something. So the thing that makes this bagging is that you're choosing from this set with replacement. So let's say, just for the sake of an example, that there are 1,000 training points here. So in bagging, you decide how many training points each one of these classifiers will get access to. So it might be 1,000, or it might be less than 1,000. You might only want each one of these to get access to 200 training points instead of 1,000. Let's kind of do a thought experiment both ways. So let's say that you allow H1 to have XTrain 1 that's size 1,000. So the thing that makes this bagging is that this is sampled with replacement from XTrain. So that means that after you randomly select an instance from XTrain to put into this bucket, it's possible to select that twice. And so what happens here is the same data point gets repeatedly drawn. And what happens is that XTrain only sees about 66% of XTrain. because of the duplications. So because of the duplications, it gets to make 1,000 draws, but there are 1,000 points here, and because of width replacement, it gets repeats. So it only sees about 66% of the data. And also let's say that there's some point here which it drew 3 times. Then that data point is represented 3 times inside xtrain1. So the training set that it gets to use is statistically a lot like xtrain, but it's a little bit different because it contains different points, and some points are repeated multiple times. So this general technique of resampling from a sample with replacement is called bootstrapping. So it's what if you decide to do it without replacement? Then if you did it without replacement, then x1 train would just be exactly the same as x train. And there's a name for that technique too. It's not called bagging, it's called pasting. But bagging is more commonly used, and it has the advantage that each one of these classifiers will get slightly different training sets. So it will increase the diversity of the final hypotheses that they produce. Even if these are all exactly the same, you're at least using different training sets. So each one of them is assigned a slightly different training set based on resampling xtrain using Bootstrap. So this one gets x3 train. Okay, and then this one gets x4 train. So you've increased diversity by giving them slightly different training sets. Another thing you can do is just randomly eliminate some of the columns. So maybe you don't want H1 to see, maybe there are 12 features or something. You're going to say, well, these guys are not going to get to see all 12 of those features. This guy is each of them is only going to get to see a random selection of 5 of those 12 features. So, and after we do this, we'll randomly eliminate all but 5 of the feature columns here, and randomly eliminate all but 5 of the feature columns there, and randomly eliminate all but 5 of the features here. So what we're doing in terms of the sklearn parameters is we're setting max features to 5. Okay, so that will further increase the diversity. Now, each one of these learning machines will select their parameters and their hyperparameters, and then they will output a best hypothesis. So H1 will be the best hypothesis produced by the learning algorithm with this hypothesis class, and H2 is the best hypothesis from there, and H3 is the best hypothesis from there, and H4 is the best hypothesis from there. And then you use either hard or soft voting, depending on which one you prefer. So you could choose hard or soft. And that gives you your ultimate hypothesis, G. And so bagging and other ensemble methods it tends to reduce both variance and bias. So when you use these simplified models, each one of these will have higher bias. So these are going to be high bias models because they're simple. They're constrained. They only have 5 features. They have less training data. So that increases bias. But then when you average them or let them vote, that gives you a hypothesis that's more sophisticated, which makes bias go back up. And the effect is usually that both bias and variance go down. Variance goes down because you're averaging a bunch of different outcomes. So this makes usually the total error go down. And almost always, depending on the degree to which you've succeeded in producing a bunch of truly diverse final hypotheses here, the error of G will be better than the error of any one of these, and also, like in the case of a random forest, the performance of the random forest will be better than the performance of any particular decision tree. So that's what we're about to see. A random forest is just bagging, where these are decision trees. Okay, so let's come back to this. Okay. So here we do the bagging classifier, and performance goes, so 92% accuracy seems to be the best that a decision tree can do. But with bagging, you can get it all the way up to 95.1. So there's also this idea, which is kind of cool, called out of bag score. So let me say what that means. So when for each one of these, so we said during this process of selecting this restricted training set that say H1 got to use. So H1 only saw 66% of the data. And then there's this other percentage that is completely virgin as far as H1 is concerned. So this gives you the opportunity to do something that's kind of like cross-validation, but it's not exactly cross-validation. So here's the whole training set, X-train. What we can do to estimate the performance of G is to go through X-train point by point. So let's say that we've selected X here. So to get a prediction on X, we'll create this G, but we won't use all of these. We'll only use the ones that have never seen X before. So maybe H1 never got to see X, and maybe H4 never got to see X. So in that case, we'll produce G just on the basis of H1 and H4. And then G will make a prediction about X, and that will be our predicted class. So you do that for every point here, and then what this builds is a set of predictions for every point in the training set. So you get if you want to call it Y train hat or something. So here's a vector of predictions for every single point in the training set, and then you can evaluate the error of this guy, and you haven't had to use the test set at all, and yet you have something that is pretty, not completely, but it's fairly unbiased estimate of the out of sample error of the ensemble method, but you actually haven't had to corrupt the test set. So this is great. So this is, when you're using an ensemble method, this is an alternative to doing cross-validation. And you can use it to tune hyperparameters the same way you would use cross-validation to do that. So here's what the out of bag score is in this case, and just the few times that I've just been playing with it here, and I've been observing that it tends to be a little bit optimistic. I don't know if there's like a theoretical reason that should be true, but so here's the test error, and it's in the same ballpark as the out of bag score. Okay, so now let's go to random forests. So now we can explain what a random forest classifier is in terms of bagging. So random forest is a bagging classifier that uses a decision tree classifier for each one of its weak learners, and these are just the settings that are chosen out of the box by sklearn. So each decision tree in the ensemble is constrained. There are at most 16 leaf nodes in any particular tree. And the splitter, I think this is saying that it's selecting features at random. So there are, how big do you want your forest to be? This is the number of trees in the forest, which by default is 500. This is the max percentage of the samples that any particular weak learner gets to see. And they're selected using the bootstrap method. So it'll be a lot like the example that we just did, where the training set is size 1000, and for each weak learner, the training set is also size 1000, but it's selected using bootstrap resampling. So it's not exactly the same as the original training set, although it is the same size. We haven't ever talked about this parameter. This means use all the cores. This is the number of cores that you want to use on the problem. If you have, eight threads or something on your machine, you can set this to 8. -1, I believe, just says use the maximum possible number of cores. And then you have to set out of bag score true if you want to do out of bag scoring. And you can see that the random forest class, well, this is kind of frustrating. The other time that I did this, these got exactly the same, these had exactly the same performance. But remember that both of them are, I mean, even if this is exactly correct, which I assume that it is because I got it from the hands-on machine learning book, building the random forest is a random process. So even if you did this exact same thing twice, the error would vary because you would get slightly different random forests. That's why it's a random forest. So random forest has the ability to rank features in terms of importance. I mean, you shouldn't put too much stock in it. There are lots of ways of ranking the importance of features. And often people that are naive about machine learning tend to have sort of simplistic views about dimensionality. Like, so here's a list in order of importance of the features in diagnosing breast cancer. So maybe some 70-year-old researcher says, well, which feature is it? What's the diagnostic criterion? And it's not a person who says something like that wants to reduce a multidimensional problem to a univariate problem, which can't be done without throwing away huge amounts of information. So it's sort of all the features in conjunction that give you all the information you need to make the highly accurate diagnosis. So where does this list come from? And to finish my thought, there are other ways of estimating feature importance that will give a list that is completely different from this one. Also, you might build the same random forest twice and get a slightly different list of best features. So where does the list come from? So every time there's a node in a decision tree, you make some kind of split, and you get an information gain, or the the Gini coefficient goes down because the weighted purity of the two child nodes is less than the purity, or sorry, is greater than the purity of the adult. So the Gini score is lower. And so the random forest can look through all of its trees, and it can see what happens when different features are used for different splits, and it can observe that certain features tend to produce splits that give you high information gain, and then it can rank them according to that criteria, which is what's happening here. From the point of view of this random forest, the most informative features for diagnosing breast cancer in this data set are the standard error of the concavity, the worst concavity, the mean fractal dimension, worst concavity. So you can kind of start really getting your hands dirty with a particular problem, which is good. If it was your job to come up with some kind of like really practically useful diagnostic test for breast cancer, you're going to have to try to deeply understand the data set that you're actually working with, and not just lazily plug the data into a support vector machine or something like that. Okay, so now we're going to move on to boosting. So boosting is like it's just ensemble methods. According to the definition given in the book, it says boosting is on any ensemble method that tries to combine many weak learners into a strong learner. So from that definition, bagging is an example of boosting. But usually, if you say boosting to somebody, they're not going to think bagging. They're going to think something more sophisticated, like Adaboost or gradient boost, which are the two kinds of boosting that we're about to discuss. Okay, so with the bagging approach, which is what led to the random forest, each one of the trees is created sort of independently at random, and with boosting, that's usually not the case. So with boosting, the weak learners tend to be weaker. So we're gonna be using some very weak learners here. In fact, we're just going to be using something called decision tree stumps. So decision tree stumps are decision trees that have exactly one node. So this is an example of a stump. So it's a decision tree, but it only splits once. And so these are the weak learners that are most often are very often used in boosting, and especially Adaboost. Okay, so each stump is gonna be created with the goal of correcting the deficiencies in the previous stump. Okay, so there's two main approaches. There are other. I mean, there's probably boosting algorithms galore out there, but all we're going to talk about is Adaboost and gradient boost. So here's the idea of Adaboost. So Adaboost assigns weights to both the training data and to the classifiers in the ensemble. So with bagging, every participant has an equal vote, but with Adaboost, each voter has like a competency score assigned to them, and their vote is weighted by their competency score. And so we said that creating each member of the ensemble here is not just independent. It's not just independent choice anymore. So each one of the voters is weighted by their competence. But as we go along in this process, the weights of the training data also change. And so competence is sort of like your weighted performance on the training set here. You might notice that these pluses and minus differ in size. And that's supposed to visually represent that these data points are acquiring increased weight. So when you evaluate the competence of the second classifier here, it's not just percentage accuracy, it's weighted percentage accuracy. So what's really important is how well it does on these more important training points. So how does a training point become more important in this process? It becomes more important by being misclassified by a lot of previous members of the ensemble. So here's the initial classifier that is, you'll notice that these pictures actually are decision stumps. So decision stumps are just inequalities that divide the data according to, it's just an inequality based on one feature. So they look exactly like this, like axis parallel half spaces. Okay, so here's the one that's initially best when all the input data have equal weights, but it makes a couple of mistakes. So now those places where it made mistakes are weighted a little bit more than they were initially. So then a second classifier is trained to have the minimum weighted performance on this training set, which is the same training set but with different weights. And then according to its weighted performance, it's assigned a certain competency score. And then you go on and so this thing made mistakes of its own. So now this data point here has decreased in importance because it was classified correctly here. So that sort of puts out the fire. But now it has its own problems, and so these things are of increased importance. And now this thing is selected so as to minimize the weighted error on those newly important points. Now, when it's time to finally make a prediction for each point, you take all of these ensemble members get to vote, but their vote is weighted by their competency score. So should we give the details? That will take the rest of class time. But I don't know. I sure did try hard to get all of this organized over the last few days. So I've maybe just indicate in the context of going through this code, somebody just in response to a Stack Exchange question implemented all of this beautifully. So you can follow this link here. I just slightly refactored the code that they wrote, but basically I completely stole it. So let's go through here, and I'll draw and try to explain theoretically what's going on here. So initially we're given training data, so x1, y1 up to xn, yn, and so you have to keep track of how you're weighting the training data. For this person's code, the variable is D, but I'm going to use capital D. So initially, the first time through, everything is equally weighted. So the weight of each training data point is just 1/n. So it's uniform distribution here. Okay. All right. So now this T is the number of, so capital T is the number of iterations here. And this is just the number of trees that number of stumps you want in your ensemble. So that's a sort of a free choice here. So the default is 500 stumps, but you could choose more or less stumps. So for each time through here, so for T equals 1 to up to capital T, you select the weak learner, HT, with the smallest weighted error. Theoretically, what you want here is, this is epsilon sub t is equal to the probability. So this D thing is like a probability distribution. So you could say, what is the probability with respect to dt that ht x is not equal, sorry, this is for the ith training data point here, is not equal to yi. So this is supposed to be an estimate of the out of sample weighted error. So the importance of each point is weighted by this probability distribution. The weighted error out of sample, but of course we can't know that because it's saying something about out of sample. So what we have is the Ensemble approximation. So to get the Ensemble approximation, you just add up all of the weights for the points that are classified correctly. So these are just the points where HTXI is actually, sorry, we're doing error here, so it's not equal to YI, divided by just the sum of the DI, or sorry, DT. Okay, so it's normalized to be something that's between 0 and 1. So this is something in the range 0 to 1. Okay, and so what this is just the weighted error, and what we're doing here is we're selecting the weakest learner with the smallest weighted error, and so that's computed over the training set like that. So where is he doing that here? So he gets a decision stump. So the max depth is 1, and so when you use a decision tree, how do you get the stump with the best weighted error? So you could almost do that by hand, you know, because each decision stump is just going to make some kind of a cut, you know, like an axis parallel cut, and you just see which one of those has, like, you know, some of those will be misclassified. So which one of these cuts has the misclassified points having the maximum total weight? So it's not that hard, and sklearn can do it for you automatically. Notice that D is a vector. You give it a vector, and so there's 1 weight for every row of X here. So now you produce your predictions, and this is getting the weighted error of this particular H. So it's just the weights. And so this just turns on the ones where the prediction is wrong. So it's just saying exactly what's in this box here. And it's kind of funny that this one is, it's not normalized, is it? So some people have slightly different descriptions of this algorithm. I hadn't noticed that before. So that's a little bit different from that's the difference between this code and the theory that I've been reading. So, but anyway, so if you're just taking the hypothesis that minimizes this, it's not going to matter whether you normalize it or not. And also, this is a probability distribution, so actually the sum is just going to be 1 anyway. Sorry, I read some confusing notes online, I guess. So you do normalize it. It's just that it's a probability distribution, so it's already normalized. Okay. So what now? So now, after we've selected the weak learner with the smallest weighted error, we're going to compute the competence score of HT. So that's the alpha t here. So alpha t is equal to 1/2. So in general, this where I write 1/2, some books like our book instead call that eta, and then they let it be hyperparameter, which is the learning rate, but we're just going to leave it as 1/2. So we do natural log of 1 minus the weighted error of HT divided by the weighted error of HT. So this will be a constant, and it'll be, just observe here that it will be positive. Okay, and let's just do some sanity check here to explore what the possibilities are. So suppose that the weighted error is something that is approximately 1. So it'll be just a little bit less than 1. So let's just do that thought experiment. So if the weighted error is a little bit less than 1, this is going to be a very small number divided by a relatively large number. So that will make this input to natural log very big. And then, so the natural log will, obviously natural log takes big numbers and just basically spits out the number of digits they contain, but still bigger is if you put a bigger number into natural log, a bigger number comes out. So in that case, the alpha t will be kind of, let's just call it big here. Okay, which is am I right about that? So if alpha t is close to 1, then you're going to get something small over something big. Yeah, so small over big is small, right? So I said something wrong. So small over big is small. So this will be something approximately 0. So when you put something that is approximately 0 into natural log, it spits out negative infinity. So it will. Oh my gosh, this is a disaster. I'm confused. So let me erase this and let's just start over. So suppose that that epsilon t is like, let's make it a particular number like 0.9. So this would be terrible. This would be very high error, right? And so then we'll get natural log of 0.1 on top, and this will be divided by 0.9. So this will be natural log of 1/9. And this will be a big negative number. Okay, so I'm confused about that because I had said I've been following some bad notes here. So in that case, this will be right. This will be a big negative number. So this is close to 0. So this will be a big negative. Okay, well that's what the math is telling us. So now suppose that the error is low, like 0.1. Then you'll get 1/2 of natural log of this will be 0.9 on top, and this will be 0.1 on the bottom. So this will be natural log of 9, which will be relatively, this will be a positive number. Okay. All right. So this is going to be positive for accurate hypotheses. That's hypotheses that have high weighted accuracy, and it's going to be negative for hypotheses that that have low weighted accuracy. Okay, so now let's make some more space. All right, and now we update the weights. So here's sort of the weight update coefficient depends on a particular training point. So let's say that I'm just going to compute this value for each training point, and it is equal to e to the minus alpha t if yi is equal to htxi. So that's if the hypothesis makes a correct prediction. So if the hypothesis makes a correct prediction and alpha is a big positive, then this will be small, right? So if alpha t is a big positive for a highly reliable hypothesis ht, then when you do e to the negative of that, that's going to be a small number because it's the reciprocal of some big positive. Okay, but this is e of alpha t if yi is not equal to the prediction. Okay, so this is the part of Adaboost where the importance of misclassified points is being boosted. So if it's wrong about a point and it has high reliability, so this is the confidence that we have in this classifier. So suppose that it's wrong and it's highly reliable, then that will be that will sort of will have this high weight increase for this particular training point. So it will be boosted in significance. All right, so finally, we update the weights for the next round. So let's go through and do that. All right, so now for the next round through, dt plus 1 is going to be equal to, let's do this for a particular training point. So for a particular training point, the training point with index I, this is going to be equal to the previous weight. So this now it will either be increased or decreased in weight, but according to the factor c x bar I, which we just described. And finally, this whole thing has to be normalized because it's supposed to be a probability distribution. So you set it equal to dt plus 1 divided by some dt plus 1. So that turns it back into a probability distribution, and then you're ready to go through and do the whole process again. All right, and so that's what's happening here. This is the part where the updates are happening. Because y is either plus or minus 1, a concise way to define this thing that we called c is yeah. So look what it's doing. It's just coordinate y is multiplying the previous probability distribution times c. So this is just c of x, but it's being done in broadcast fashion because the this prediction, okay, so yeah, so will the signs be the same or not? So if it's correctly predicted, then the product of these two will be plus 1, right? Because y and the prediction will agree. And so then you'll have this, which is what we did when we case-wise defined C. But if y and the prediction disagree in sign, then it'll be negative and change this to a positive. So it's exactly what we talked about earlier. So here it's just broadcast multiplying D and C, and then it's normalizing, and it's remembering the hypothesis that was the best. So this is remembering HT, which was the champ of round T, and then it's remembering the confidence score that belongs to that particular champion. Okay. So now that is sort of the training process, or the process for selecting the forest. So we just built the forest of stumps. And now that we have the forest of stumps, how do we use the forest of stumps to make a prediction? Okay. So to make a prediction, you just do the prediction y hat is the sign of the sum over the entire ensemble. So this is t equals 1 to capital T of alpha t. So alpha t is the confidence score for the teeth hypothesis, htx. Okay. And as we sort of figured out as we went through here, it's possible for this to be a negative, which I didn't understand. I'm sorry for being confused about that. And so where is that stuff in the code? It is, let's just get rid of this completely. Right here. So this y equals, so initially y is all zeros. So this is a little bit confusing because it's happening in broadcast fashion for the entire matrix X. So this is making a prediction simultaneously for every row of X. So initially y is 0, and then we go through for each hypothesis in the ensemble. And we add to the previous, we update y by adding in the confidence in H times the prediction of H. And then we take the sign of that. So this is just the broadcast version of the math that we just erased from the screen. Okay, and that gives us our highest score yet. So it beat bagging. It got 96.5 as its accuracy score. Here's I made a debug version that keeps track of the weights, so you can see what happens to those over time. And I thought we would just go through it and look at a toy version. So instead of using all of the training data, let's just use 75 points, which is pretty small. And now let's just use an ensemble that has 5 members. So even with this incredibly weak configuration, look at the test accuracy. It's still better than you can do with a single decision tree, isn't it? Or was a single decision tree, I think this run, it got up to 0.92 or whatever. Anyway, so this is so little work that you could almost do it by hand. But we're just gonna look and see what happens in Adaboost as this happens. So we're gonna produce a forest with 5 stumps. And this output shows you what happened as Adaboost ran. So initially we have the 0th stump. So it makes this decision based on the mean parameter. Initially the weighted, so this is what the weights look like before the stump is introduced. So initially everything is equally weighted. And these are the misclassifications. So most points are not misclassified, except that there are, with this stump, it makes a few misclassifications, you can see there. So now the next time through, this is like t equals 1 now, who was t equals 0 before, we produce another stump. And the weights for the data that was correctly classified have gone down, but the weights for the misclassified points have gone up. And now this stump has its own misclassifications. So it has more absolute misclassifications, but its weighted score is best among all possible decision stumps, and it's assigned a weight. So this is the alpha t that belongs to this stump. And we keep going. So now the things that have been classified correctly a few times in a row have very low significance. You know what I just realized about that alpha t being positive thing? It might, that might be using the weak learner assumption, namely that it's at least 50% correct. Or that would mean that, you know, I think that's probably what was going on with the idea that alpha t is a positive number. Alpha t will probably be a positive number as long as the weak learner is at least 50% correct. Okay, anyway. So now you're getting some diversity here because this point has been misclassified a couple of times. This has been misclassified once, and a lot of these have been misclassified 0 times. So you're getting sort of different weights and the 75 training points. This thing has its own misclassifications. The weight here is a little bit lower for this guy. Then we make stump 3, and here's the weighted data. And now this point is getting quite angry because it's been misclassified, I think, 3 out of 4 times. So of all the probability weight you have to assign to the entire training set, 40% of it is allocated just to this one point that's been a problem. And so then that stump gets this alpha t score, and this is the last one. So the previous stump managed to correctly classify this problem point, and so its weight has gone down. And this process can just continue as long as you want it to. It can even keep going after the training accuracy is 0. There's no reason to stop because it just keeps refining itself. So here it is from the library, the hand implemented version. In this run, just it's a random process, but in this run, the hand crafted version did better than the library, which is always exciting. So this too can weight feature importance just by looking at which stumps tend to occur often. And great. So then I was going to talk about gradient boosting, but we don't really have time to talk about gradient boosting. But maybe we'll do that really quickly next time. So let me stop this and stop recording.